Hello, am I audible?
Yes, sir.
And my screen is visible, right?
Yes, sir.
Okay. So, welcome everyone to the week 8 discussion of this course, Introduction to Machine Learning. And this course was originally taken by Professor Balaraman Ravindan, Professor and Head of the Department of Data Science and Artificial Intelligence, IIT Madras, and myself, Ayan Paul. I am a PMRF Research Scholar from IIT Kharagpur, and I am a PMRF TA for this course. And my duties are I will solve you some question that will help you when you will solve your weekly assigned questions. Okay, but before that I will discuss some of the theory part so that your concepts will be more clear. Okay, so so in week 6 we have discussed about decision trees. Okay, in week 7 we have discussed about ensemble methods. Okay, so today we will combine the knowledge of both week 6 and week 7, and we will discuss something about random forest. Okay, what was the problem with decision tree? The problem with decision tree is they work great with data used to create them, but not flexible when it comes to classifying new samples. Means they are more prone to the training data. But when the testing data or a new data set is given to it, it is okay, someone is joining. Just wait a minute. Okay. So the problem with the decision tree is they work great with the data used to create them. Okay, so they work very good with the training data, but whenever the testing data or a new data set is given to them, they are not able to they are not very flexible, or they do not work well. Okay, so this is the main problem with decision trees. Okay, what's the problem? So to get rid of it, we have introduced a new machine learning model called random forest. What does random forest do? Random forest combines simplicity of the decision tree with a with flexibility, resulting in vast improvement of accuracy. Okay, so random forest concept is we will combine many decision trees and we will create a forest. Okay, so last week only I have told you about ensemble methods, right? So the concept of ensemble method is if we join many weak learners together, then we can create a strong learner. So same thing. So what we are doing, we are utilizing many decision tree, and we are applying an ensemble method so that we can create a forest, and we get better accuracy. So random forest is a classifier that contains a number of decision tree on various subset of the given data set. Okay, so now what are the steps to create create this random forest? So first we have to create a bootstrap data set. So let's say this is our original data set. Okay, so yeah, this is our original data set. So we have 1 2 3 4, we have four variables or four input variables. First is chest pain, second is good blood circulation rate, third is blocked arteries, and fourth is weight. And by this four input variables, we are predicting our output variable, that is heart disease. Okay, so this is our true data. And now we will now our first step to create the forest is to create a bootstrap sample. I have already talked about bootstrap sample in the previous class. In bootstrap sample, what we do is we create a data set with same number of data points, but we do it with sampling with replacement. Okay, so what we will do, we will take the same number of data points, mean same number of rows. Here are four rows, so we will in the bootstrap sample also we will have four rows. But what we will do, we will resample the data with replacement, means one row can be repeated multiple number of times. So by that we will create a bootstrap sample. Okay, now you can see this is the bootstrap sample. We have created this bootstrap sample. Okay, now what is the second step? Second step is create a decision tree using the bootstrap sample, but only using a random subset of variable at each step of creating the tree. Now you might have remember whenever we were discussing about decision tree, and whenever we have created decision tree with that information gain or Gini index, anything. So what we have done, we have considered all the four variables, right? Means all the input variables, and then we have found out the Gini index or information gain of each variable, and whichever variable information gain was maximum or Gini index is minimum, we take that as root node and then repeat the process again and again. Okay, so by that we have created a tree. But in this random forest, what we will do, we will create a tree, but here what we will do is we will take a random subset of variables. Means we will not take all the, like here there are four input variables, right? But here in creating this decision tree of this random forest, we will not take all the four variables. We will take the subset of variables. We may take two variables or three variables at a time, and then we will create a tree. Similarly, in the next step also, whenever we are this is the root node, right? Whenever we are selecting the this branch nodes also, we will do the same process. Means we will only take a subset of our input variables, not all the input variables, but we will only consider a subset of input variables, and we will create a tree of this bootstrap sample. So after this, a tree of the bootstrap sample is created, we again go to the step 1. We will again create a bootstrap sample, and we will repeat the process n number of times. Okay, so generally here we repeat the process 100 or 1000 number of times. 100 is ideal. Okay, so we can repeat this process 100 number of times, and we will create this forest. Okay, so you can see one tree. This is one tree. This is the second tree of a second bootstrap sample. Okay, this is the second tree of a second bootstrap sample. Third tree from the third bootstrap sample. Similarly, we can create 100 number of trees, and then we will predict the final output based on the majority of prediction from each tree. So each tree we will get some prediction. So based on the majority of prediction, our final prediction, we can have our final prediction. So random forest is an example of bagging. The bootstrapping we are doing, and lastly when we are aggregating the result by voting from each random decision tree, that is known as bootstrap aggregating or bagging. So random forest is an example of bagging ensemble technique. So I have already told you, forest we have to create by many number of decision tree, and whenever we are doing this, means we are combining different weak learners to form a strong learner, that is known as ensemble method, right? And ensemble method, the ensemble method here we are using is bootstrap aggregating or bagging. Okay, so this is bootstrap aggregating, right? We are creating different bootstrap dataset, we are creating tree of each dataset, and then lastly we are aggregating the result to get a final prediction. So that is how we are creating a random forest. Okay, so is it clear to everyone?
Yes, sir.
Okay, so this is about random forest. Okay, so yeah, we can combine many decision tree by one method, that is random forest. Now here we are using bagging, right? But we can also use boosting also, right, to combine this decision tree and use boosting also. So that gives us two two methods. Okay, yeah, that gives us to two methods called AdaBoost and gradient boost. Okay, in both this method also we are combining different type of tree, and we are combining different type of weak trees to form a machine learning models, which will give us more accuracy or less variance, whatever. So here in the previous example, when we are creating random forest, we have used this method called bagging. But in this slide or the next slide, we are using boosting technique. Okay, so boosting technique, we can make two type of this models. One is called AdaBoost, and second one is called gradient boosting. So AdaBoosting, so this is AdaBoost. AdaBoost, it is an ensemble technique where each weak learner is developed as a decision stump. So here we are creating a tree of the bootstrap sample, but here we will start with only a stump. What is a stump and what is a tree? Stump, tree means it will have many branches and it will have many leaves, right? That is tree. But stump is it will have one root node and only two leaves. Okay, so that is known as stump. Okay, so stump is a tree with just a single split and two terminal nodes. These leaf nodes are also known as terminal nodes, right? So they are used to classify the observations. We will be taking data. We will be sampling it by any process, or we will take the whole data, and what we will do, we will make different stumps. Okay, we will not start with tree, but we will start with stumps only. Stumps means it will have one root node and two leaves, so that is known as stump. So in contrary to random forest, each classifier has different weights. In random forest, when we were aggregating, we are giving same weights to all the trees. Means if here let's say yes will come, here no will come, here yes will come, yes will come, yes will come, yes will come, because we have two decision, right? Yes heart disease or no heart disease. So let's say from here we are getting yes, from here we are getting no, from here we are getting yes, from here we are getting no, whatever. Like six trees are there, four tree we are getting yes, two tree we are getting no. So our decision will be yes only. But here what we are doing, we are giving that means here we are giving same weight to each tree. Means each tree has a same say in prediction, but not here. Here we will give different weights to our different tree based on the accuracy. Okay, we will test the accuracy, and according to it, we will give different weights to different trees. Means the trees which are more accurate, we will give more weight to it. The tree that are less accurate, we will give less weight to it in the final prediction. Here each classifier has different weight assigned to it based on the classifier performance. That is, more weight is assigned to the classifier when accuracy is more, and vice versa. Now weights are also assigned to the observation at every round. Boosting, whenever I have told you the concept of boosting, I have told you that boosting means we will make one classifier, we will take the we will see how many points are misclassified and how many points are classified. The misclassified ones we will give more weight, so that more weight, and the classified ones we will give less weight, and we will create a same we will create a data set with same number of data points, and then again we will apply this classification process, or apply a classifier. So here also what we are doing, one thing is we are giving weights to different tree, means more accurate the tree, more we will give weight to it. Secondly, we will also give weight to the weight to the misclassified points, means the points which are more misclassified, we will give more weight to it. The data points which are classified well, we will give less weight to it. And again we will create a stump. Now again we will create a stump. Similarly, we will like random forest, we may repeat the process to 100 times, and then again we will do the same thing, that is prediction. Okay, prediction, here we will here weight is also added to prediction, means here the more accurate is the stump, the more weight we will give to it, and less accurate the stump, the less weight we will give to it. So this is a this machine learning model is known as AdaBoost model. So any doubt in this? Any doubt in the AdaBoost model? Am I audible?
So more weights for the accurate stumps as well as the misclassified points, is it?
Yeah, yeah.
Okay.
Two weights we are giving. One, we are giving weights to a classifier, and second, we are giving weights to the data points. Okay, the weights to the data point, that is the concept of boosting, right? That about it we have discussed in the previous class. That is how boosting works. It will take a classifier, it will see what are the misclassified points and what are the classified points. Then it will give more weight to the misclassified point and less weight to the classified points, and it will create a next data set based on these weights. Okay, so we are giving weights in two sets. One, we are giving weights to the stump, and secondly we are giving weights to the data point source. Okay, the second thing is a main concept of boosting. The first thing we are used for this AdaBoost process. Okay.
Okay, sir.
Okay, so AdaBoost is clear. Now what is this gradient boosting? Okay, someone is joining. Yeah, so gradient boosting is an ensemble technique like AdaBoost. It starts with a leaf that predicts the average output, regression or log odds classification. Then residuals from the current classifier becomes the input from the next for the next classifier, building trees step by step. And then learning rate helps in capturing, okay, usually GB. Okay, so gradient boosting, yeah, our this AdaBoost, it start with a stump only, but gradient boost starts with a leaf. Okay, what is this leaf? This leaf is the mean or average of the if we are doing regression, then it is the average of the regression value, or it is the average of the log odds. Log odds, you can refer to that logistic regression, their formula and everything is there. So it will basically average the outputs in case of regression, or it will average the log odds in case of classification, and by that we will first create a leaf of it. Then the residuals of the current classifier becomes the input for the next classifier, building tree step by step. Okay, now next thing what we will do, once we get the this leaf. Okay, this leaf will have nothing but the average of the output. Okay, average of the output, average of the log odds. and by that we can find the residual. What is residual? Residual is your average minus the output. Minus the output means here means if you have three data 5, 7, 8, so we will take the average 5, 7, 8. Okay, 5, 7, let's say 5, 7, 6, let's say 5, 7, 6. Okay, let's say 5, 7, 6. Okay, so 5, 7, 6, what is the average of it? 5 plus 7 plus 6, that means 6 is the average. So we will take the residual. So residual of this is 1, residual of this is again 1, and residual of this is 0. Now we will form our tree on the basis of this residual only. Okay, we will not consider this values, but we will consider the residual only, and by that residual we will build the tree. Okay, so the residual from the current classifier becomes the input for the next classifier, and by that we will build the tree step by step. Now again as this is a boosting technique, so boosting technique, what we will do, it is a sequential process, means we will create a one tree, then we will see what is the error from that, and we will try to decrease the error step by step in each tree. So similar thing we will do here. So we will take the residual, on the basis of the residual we will create a tree here. Okay, now again on the basis of residual from this we will create a tree here, and we will keep on adding the tree. We can add like up to 100 trees, and then we will do the final prediction here. Learning rate has to capture maximum variance by adjusting the model gradually, and it moves in opposite direction opposite to the negative gradient to reduce loss, similar to gradient descent. Now here as this is a gradient boosting technique, so we use the concept of gradient descent. What we do in gradient descent, we have two values like 5 and 10. We have two values, right? So we will first take the range of it, or 10 minus 5 will be 5, and then this 5 values we will 5 values we will divide it into small steps. So that is the learning rate. Okay, that is the concept of learning rate. The concept of learning rate you can revise in your perceptron learning algorithm, right? So there, what is the weight? The new weight Wn will be equal to the original weight, okay, plus something learning rate plus delta something. Okay, so we are what we are doing, we are adding a learning rate, and adding or subtracting, whatever we are searching the process, means our maximum may come in between 5 or 10 somewhere like that. So we will keep on searching. From 5 to 6 we will search, from 6 to 7 we will search, and 7 to 8 we will search, 8 to 9 we will search. Whenever we are going from 8 to 9, what will happen? Our error will increase as we have to go to 8, right? So whenever we will go to 5 to 8, our error will decrease, but when we cross 8, when we cross to 9, our error will increase. So we will say that this 8 is the minimum value. So this is the concept of gradient descent method. So here also we are what we are doing, we are calculating residuals, and our target is to reduce the residual again and again. Okay, so in first tree we will reduce this residual, like this is 110 is the residual. So creating first tree we will reduce the residual to some extent, then again we will reduce the residual to some extent, again we will reduce the residual to some extent, till we will keep on reducing the residuals until we reach our target, or we will say this is acceptable. So up to that we will keep on reducing the residuals. So that is gradient boosting. So usually in GBM every tree is grown with 8 to 32 terminal node. Like here we are using AdaBoost, here we are using stumps. So stumps has 2 leaf or 2 terminal nodes, but here in this gradient boosting we are using 8 to 32 terminal node, means the terminal nodes will be 8 to 32, and around 100 trees will be grown. Similar like random forest or AdaBoost, we will keep on growing trees one by one. But here, unlike AdaBoost, AdaBoost we have given weights to the tree also, right? Like the more accurate the tree, we are giving more weight. The less accurate the tree, we are giving less weight. But here, each tree will be given equal weights. So this is the concept of gradient boosting. So what is the difference between AdaBoost and gradient boosting? So first thing, AdaBoost starts with a stump only, but here this gradient boosting starts with a leaf. Second thing, in AdaBoost we do not grow complete tree, we grow only stumps. In each step we grow only stumps, but in gradient boosting we grow a tree. But like AdaBoost, we are scaling the tree. We are scaling the tree to a leaf. Means we cannot grow a tree more than a leaf. Here also we are scaling the tree, but here we are scaling the tree such that we have 8 to 32 terminal nodes. So that is the difference. Third difference is in AdaBoost we are giving more weights to more accurate tree and less weight to less accurate tree. But here we will be giving equal weights to each tree. So this is the difference between AdaBoost and gradient boosting. So any doubt?
So that searching between 5 and 10, you were saying that I didn't get that.
Yeah, this is known as gradient descent method. Like you are searching this space, right? And you have to search the minimum. Okay, so you are searching from here to here, means this is your initial point, this is your final point, right? So what you will do, you will keep on you will first divide your subspace to equal number of parts. And how we divide a subspace? By a thing called learning rate. Means we cannot say like this is your 5 and this is your 10, so and this 8 is your target point, right? So you cannot say like you will go from 5 to 10. You will directly grow from 5 to 10. If you will directly go from 5 to 10, you will miss 8. So that is why, that is the concept of learning rate. In learning rate, what we will do, we will divide the subspace into equal number of small steps. Now equal number of small steps, let's say we are dividing it into 5 equal steps, means 5 to 10 we are dividing to 1 equal step. So after 5 we will search 6, we will search 7, we will search 8. Okay, after that whenever we will search 9, our error will increase, right? From 5 to 6 the error will be something from whenever we will be searching 6, our error will be something because 8 minus 6 is 2, so our error will be large. Now 8 minus 7 when we'll do, it will be 1, so error is small. 8 minus 8, error is 0. Now again 9 minus 8, error is again increasing. So that is the concept of gradient descent. Whenever our error is increasing, we will terminate the process. So we will say the 8 is our target point. Okay, so that is the concept of this gradient descent method. Okay.
Okay, sir. So that gradient is actually the error. We are trying to minimize the error, right?
Yeah, gradient
Okay.
is nothing but error, right? Gradient is delta of
Yeah.
something by delta of your input, del something by del x. So that is gradient. In weights you might have seen it is something by del w, right? Del something by del w. Whenever we have told about neural network, that is del something by del w, right? So that is the descent. That is the gradient. Okay, and gradient descent means we have to decrease the gradient again and again. So that is gradient descent. Okay, clear, right? Okay, now this is all about ensemble methods. So first we have discussed about decision tree in class 6, then we have talked about ensemble methods, then we have seen how these ensemble methods are used in creating a forest from from many decision tree. So we can do both by both the ensemble method, bagging as well as boosting. Bagging, the whenever we are using bagging with the decision tree, that machine learning model created is known as random forest. Whenever we are using boosting, we can create two type of machine learning model. One was AdaBoost and second one was gradient boost. Okay, and now we will learn about a new model called a Bayesian network. Okay, so what is this Bayesian network? A Bayesian. Okay, someone is joining. Okay, so Bayesian network. A Bayesian network, also known as Bayes network or Bayes net or belief network or decision network, whatever, is a probabilistic graphical model that represents a set of variables and their conditional dependency via a direct acyclic graph. So this graph this graph you are seeing, this is known as directed acyclic graph. Okay, our DAG contain a set of nodes and links where each links represents relationship between the nodes. Okay, each link will represent a relationship between nodes. So these are nothing but, you can say, these are random variables. Okay, this 1 2 3 4, these are random variables, and this links represents a connection between this different random variable, and this type of network is known as Bayesian network. So again, a Bayesian network, it is a probabilistic graphical model that represents a set of variables. These are, you can say, set of variables or random variables, and their conditional dependency. And whenever we are connecting two nodes by links, so we are doing nothing but we are giving a conditional dependency between these two nodes. Like one is whenever we are linking this 1 with 3, so we are giving a conditional dependency that 3 is dependent on 1. So so this type of network is known as Bayesian network. Our DAG contains set of nodes and links where each link represents a relationship between the nodes. Okay, so this is a probabilistic graphical model. So we need to discuss something about probability types. So there are two types of probabilities. One is joint probability and another is conditional probability. So joint probability is a measure of two events happening at the same time. That is, if you will say P and B, the probability of intersection of A and B may be written as P A intersection B. So joint probability means both the events are happening at the same time. Means, if let's say 1 is a event, then 3 is a event. So if we are talking about joint probability, then 1 and 3 are happening at the same time. And how we will write a joint probability? That is P and B. P and B, and symbol is and symbol, this is the intersection symbol or and symbol. So P A and B. So that is about joint probability. But whenever we are talking about Bayesian network, we are interested in a conditional probability, not joint probability. We are interested in a conditional probability. So this conditional probability of event B is the probability that the event will occur given that event A has already occurred. Means, if I say the conditional probability of 3, so that is the probability of 3 given that 1 has already happened. So that is conditional probability. So B given A, that is read as P B given A. So that is probability of event B occurring given that event A already occurred. Okay, so we are interested in probability of B such that event A has already occurred. Now if A and B are dependent events, then if A and B are dependent events, then we can write it as P A and B and divided by P A. If A and B are independent events, as we are talking about independent events most of the time, so that we can write as P B given A as P probability of B. Why probability of B? Because this is probability. Yeah, here I can explain you. This is PBA, right? PBA. So PBA will be equal to P A intersection B divided by P A. So that is the formula, right? But if A and B are independent events, so what happens is P A intersection B will be equal to P of A, probability of A, into probability of B divided by probability of A. So probability of A and A will get cancelled out, so we are left out with probability of B given A. If this is an independent event, then it is probability of B only. So this is between this is about joint probability and conditional probability. Now here, as we are talking about the Bayesian network, so it is important to know what is a Bayes theorem. So Bayes theorem you must have heard again and again, but again it is better to discuss it. Bayes theorem. So Bayes theorem gives a mathematical rule for inverting conditional probability, allowing us to find probability of a cause given a effect. Okay, so if I say here if I say b by A we have find out, right? So let's say B is a B is a effect and A is a cause. So if we have effect given cause, then Bayes theorem, what we can find out is we can find out cause given effect. So how we can find out? We can find out by this formula, that is PA given B is equal to PB given A into PA divided by P of B. Okay, that is Bayes theorem. Now where A and B are events, yeah, PB is not equal to 0, because you know that denominator cannot be 0. If denominator is 0, then this thing will become infinity or not defined. So PA given B is a conditional probability, the probability of event A occurring given that B is true. So that we have already discussed in conditional probability, that what is PA A given B, that probability of event A given that B has already happened. So it is also called posterior probability of A given B. Okay, now what is PB given A? PB given A is a conditional probability, that probability of event B occurring given A is true or event A has already happened. It can also be interpreted as likelihood of A given that fix B. Okay, it can also be written in the terms of likelihood. Okay, probability of B given A can also be written in the term of likelihood, that is likelihood of A given B. Okay, so probability and likelihood, you can say it is an inverse type of thing, that probability of if B given A, then you can say likelihood of A given B, or likelihood of A when B is fixed. So that is PB given A. Now what is this PA and PB? PA and PB are probability of observing A and B respectively without any condition. That is, PA and PB are independent probabilities. There is no condition in it. So P A given B or PB given A are conditional probabilities, but this PA and PB are only probabilities of A and B without any condition. They are also known as prior probability or marginal probability. Okay, this A given B is also known as posterior probability, right? But this is known as prior probability or marginal probability. Okay, so is this clear? All the terms? Now about Bayesian network, the probability of random variable depends on their parents. Okay, so probability of all the random variable will be depending on their parents. Therefore, we can formulate a Bayesian network that p x1 x2 xn can be written as p xi by whatever their parents are, parents of xi, into p x2 into parents of x2 into p x3 into parents of x3, like that we can write. Okay, so that is a Bayesian network. So any doubt in this? Any doubt? Am I audible? Hello?
Yes, sir, no doubt.
Okay. So no doubt, right? What is a Bayesian network? What is a DAG? DAG is directed acyclic graph. Okay. A directed acyclic graph means one node is directing towards another node. So that is what directed acyclic graph. Whenever there will be arrow in any such graph, so that is a directed graph. And why it is acyclic? Because it is not forming a cycle. Okay. If it is forming a cycle, then it is called a cyclic graph. But as you can see, this is not forming a cycle. That is why it is known as directed acyclic graph. So what is a Bayesian network? Bayesian network is a probabilistic graphical model that represents a set of variable and their conditional dependency via a directed acyclic graph. Okay. Now as we are talking about probabilistic graphical modeling, so again we need to know about this probabilities. So probabilities, one is joint probability and another one is conditional probability. So we generally talk about conditional probability. So what is conditional probability? Condition probability is probability that an event is happening provided something has already happened. So that is conditional probability. So this Bayesian network uses this Bayes theorem. So that is why this is about Bayes theorem. So Bayes theorem is Bayes theorem gives a mathematical rule for inverting conditional probability. Means if we say B is our effect and A is our cause, then what we will do, we can invert the conditional probability, that we can find the cause provided that given the effect, that we can find out by this Bayes theorem. And again there are some terminology that you should know. One is conditional probability, you have already know. This conditional probability were also known as this posterior probability, and we have this individual probabilities like PA and PB. This PA and PB are known as marginal probability or prior probabilities. So up to this it is clear. Now what this Bayes theorem do is, Bayesian network do is, the probability of a random variable depends on their parents, because there is a probabilistic relationship between the parent and the child nodes. So the probability of the child node will be dependent on the parents, and we can write this as, if we want to know probabilities of different nodes, so we can write it as probability on one node given their parent into probability of next node given their parent into probability of third node given their parent, and so on. So this is about Bayesian network. Okay, is it clear? It is clear, I think, right? Okay.
Yes.
Now there is a d-seperation rule. This Bayesian network, we are doing, we are computing relationship between different nodes, right? These nodes are also known as vertices, and these links are also known as edges. So don't get confused. These things will be used again and again. So again I am repeating, these are nodes, and this arrow is known as links. Okay, because it is linking two nodes. These nodes are also known as vertices. This arrow or links are also known as edges. Okay. Now we will see a technique called d-seperation. So what is this d-seperation? It is a concept in Bayesian network that has to determine whether two variables are conditionally independent given some set of other variables. Okay, so two variables, if they are far apart, so what we want to check, if they are far apart of, or they have nodes in between, what we want to check, if they are conditionally dependent or independent. So it stands for directional separation. D-separation means directional separation, and is used to analyze the dependency and independency in the direct acyclic graph. Means this d-separation technique, what it will do, it will help us to know the dependency of independency of two nodes that are far apart. Okay, so there are three rules of d-separation. First is chain structure or linear causal chain. So we have three nodes, x, m and y. So these are the arrows directed towards it. That means this is nothing but x, then m, and then y. Okay, x, then m, then y. Okay, erase it, write it well, x, m and y. Okay, so in this case x influences m and m influences y, because the parents all influence their child, right? Yeah, there are two type of nodes here. Let me see, these two are parents. Okay, because these are also known as parent nodes, or they are also can also be called as root nodes, and this 3 is the child of 1 and 2. So this 3 is a child node, or also known as branch node or anything. and last node is also known as terminal node, like in a decision tree. So this x, m and y, so m is the child of x, or x is the parent of m. Similarly, y is the child of m, or m is the parent of y. Okay, so this is the relationship between x, m and y according to our chain structure. Now in this case, x influences m because x is the parent of m, so x influences m and m influences y. So this is clear from the graph itself. Now if m is not given, that means if m is not given, then x and y are dependent. Okay, knowing something about x will give information about y. So if this m is not given, okay, uh, m is not given, or we can say if we do not know anything about m, or m is just a random variable, then x and y are dependent, because x depends on m and m will depends on y. So this x and y are dependent. But if m is given, okay, m is given, then m is not a random variable, but m is rather a constant. Okay, if m is given, then x and y are independent, because this m is blocking the path between x and y. That is why x and y will be independent. So once we know m, additional information about x doesn't help us to predict y. Okay, because the influence is blocked at m. So so this is about chain structure rule. So again I am telling, chain structure rule, x, m and y. So x, m will be dependent on x, y will be dependent on m. So that is the chain structure. So there are two conditions if m is given or m is not given. So if m is not given, then x and y, x and m is not given, means m is a random variable, then x and y will be dependent. But if m is given, then this m will block the path between x and y. In that case, x and y will be independent. So conclusion, in a chain structure, the middle variable blocks the path when conditioned on it. Condition on it means if it is given. Okay, that is conditional probability, right? If it is given, it is also known as condition. So conclusion, in a chain structure, the middle variable blocks the path when conditioned on it. The second rule of d-separation is Fox structure or diverging causal chain. Here it is m. Okay, let me erase it. Okay. Now here uh, m will influence x, and sorry, m. Okay, let me erase it. Okay. Now here what is the case here? M, so, okay, x will influence m and x will influence y. Okay, so x influences both m and y. So x is the common cause for both. Now if x is not given, again if x is not given, then m and y are dependent. Why m and y are dependent? Because x influences both m and y. So if x is not given, m and y are dependent. Knowing something about m gives information about y, because both depends on x. And second case, if x is given, then m and y are independent. Once we know x, knowing more about m gives no further information about y, because their shared cause x is known. So conclusion, in a fork structure, the common cause, the fork point, blocks the path conditioned on it. So this chain structure and fork structure are very similar. Here they tell the same thing. If something is in between and it blocks the structure between this two nodes, then we can say that these two terminal nodes are independent of one another. Okay, so this is a chain structure rule, and this is a fork structure rule. Now we have a third rule known as collider structure rule, or known as V structure or converging chain. Here what will happen is, here it is similar to the first, but only the arrows are pointing towards m. Okay, so in this structure, both x and y will influence m. So m is the common effect of both x and y. Earlier x influences both m and y, but here m is influenced by both x and y. Now here the thing is reverse. Okay, if m is not given, x and y are independent. Okay, if m is not given, then x and y are independent. But in chain and fork structure it is reverse, right? If the middle thing is given, then both the terminal nodes are independent. But here it is reverse. Here if m is not given, then x and y are independent. Okay, and if m is given, then this x and y are dependent. So conclusion, in the collider structure the path becomes open. Dependency is introduced when the collider or any descendant are conditioned on. So simply you can simply remember this. In a chain structure, what will happen is, if a middle node is given, then this both terminal node will be independent. Same in is case of fork structure, that if the middle node is given, then this both the node are if the middle node is given, then both these nodes are independent. But in collider structure, if the middle node is given, then both the nodes are dependent. Okay, both the nodes are dependent. Okay, so that is the difference between this chain structure, fork structure, and collider structure. It is all depend upon the arrow. Okay, arrow pointing, where is the arrow pointing? So by that we are deciding which node influences which node. So these are the three techniques of d-separation or directional separation. Okay, so is it clear? Is it clear? Am I audible?
Yes, sir. So that tree, when you construct, so these rules you will apply to
Yeah, 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 yeah,
ensure
yeah, yeah,
directional
yeah.
separation.
Exactly. We will be solving a question also, so there it will be more
Okay.
clear. Okay, now another thing is about parent-child relationship. Only this d-separation rule is only used in parent-child relationship, but still it is better to discuss one by one thing. So first thing is a direct parent-child dependency. Okay, so A is a parent of B or B is a child here. So in a Bayesian network, if there is a directed H from A node to B node, then A is a parent of B or B is the child of A. So this indicates that value of B depends directly on A. More formally, we can say with the help of conditional probability distribution, and B is expressed as probability of B given A, because A is the parent and B is the child. So we are interested to know the P B given A. Okay, so that is about direct parent-child dependency. Again here you can see A is the parent of B, B is the child of A, and again same thing it is written. Now second thing is multiple parent for one child. Now here you can see, here this is the graph, A and B, and they have a common child. Okay, they have a common child C. A and B are the parents, two parents, and they have a common child C. So multiple parent for one child. So when this case happened, a child can have more than one parent. In such cases, child is conditionally dependent on all its parents. Like here, what we are writing, P probability of B given A, right? Now here what we will write, probability of C given A and B both, right? This is what we will write, probability of C given A and B, because C is the child and it will be dependent on its parents. So C, probability of C given A and B. So here C has two parents and A and B. The probability of C is conditional to both A and B, that is probability of C given A and B. Knowing both A and B will give us information about C. Now third thing, it is the independent children given uh, parents. Okay, independent children given parents. So here you can see this is A has child B also, and A has child C also. A has child B, A has child C, and B has child B has child C. A has child B, A has child D. Okay. So here in third case, A has two children. A has child B and A has child D, and B has a child C. Okay, this is the graph. Now here in Bayesian network, children are conditionally independent of each other given their parents. So if A is given, then B and D are independent. B and D are conditionally independent. This is a critical feature of a Bayesian network, and it is used to simplify computation. So this is the case of what? This is the case of this only. Okay, x m or Fox structure only. Let's say x is your parent and m and y are the two children. Now if x is given, then m and y will be independent. So same thing. So independent children given parents. So you can see b and d are the independent children and they have a parent. So if parent is given, then b and d will be independent. So B and D are children of A. B and D are conditionally dependent of each other given A. Knowing A makes B and D dependent. Without A and B, D could be dependent due to their shared influence on A. So same thing as this Fox structure, but here it is more clear in case of this independent children given parents. We have a fourth case, explaining away influence via a shared child. So now we are talking about this collider structure rule. So what this collider structure rule say that if we have two parents and one children, this m is the children, and we have two parent x and y, then given this m, this x and y becomes dependent. So if we are given the c, then this parents becomes dependent. So here same thing it is written, if two variable parents of a common child and child is observed, the parents may become conditionally dependent. This is called explaining away effect. If c is given, then a and b will be dependent, not independent, but a and c will be dependent. So same thing written here. Now third, or the grandparent children dependency, that will be our first case of this chain structure rule, x m y. So given m, this x and y will be independent. So same thing, if b is the parent, a is the b is the b, let's say parent, a is the grandparent, c is the grandchildren, then a and c will be independent given the b. So that is what written, a is the grandparent of c and b is the parent of c. If b is given or the parent is given, then grandparent and the children will be independent. Okay, this is done by our this chain structure rule. Okay, so is this clear, this 5 examples of the parent child relationship? Is it clear? This things is derived from your d-seperation rule only, but it is better to have a more clarity. That is why I have given in terms of 5 cases. So is it clear or not clear? Any doubt in this? No doubt, right? Okay. Now let's move to an example of a Bayesian network. So this is a popular example of that burglary earthquake alarm question. Okay, so this is a popular example of a Bayesian network. So here this burglary and earthquake are your parent node, or they can also be called as root node. Okay, this two are root node. This alarm is your hello. Okay. So yeah. So this burglary and earthquake is your root node, and this alarm is the child node of burglary and earthquake, and John cause and Mary cause are the child of alarm. So here this is forming a Bayesian network. So what exactly is someone has installed an alarm, and this alarm will be will get ring by burglary or earthquake, and this person has two neighbors, John and Mary. So whenever the alarm will ring, both the neighbors, John as well as Mary, will inform the person who has installed the alarm. Okay, so we have the probability of burglary is given, and probability of earthquake is given. These are prior probabilities or marginal probabilities. Why these are prior probability or marginal probability? Because these two nodes are the parent node, or you can say these two are the root node. Means these nodes are not influenced by any other node. That is why we are using prior probability only, and not prior probability or marginal probability only, and not conditional probability, because these two nodes are not influenced by any other node. So that is why we are using marginal probability only. Now about alarm. Okay, alarm is dependent on these two parents, burglary as well as earthquake. Okay, so we have two parents, that is why we will write conditional probability as probability of alarm given burglary and earthquake. So we have this truth table. This is also known as truth table, or you can say Boolean table, anything you can tell. So here, if burglary also happens and earthquake also happens, then probability of ringing alarm is 0.95. Then burglary happens but earthquake doesn't happen, then probability of alarm will ring, that is 0.94. Now probability of burglary does not happen and only earthquake happen, the alarm will ring as 0.29. And then both are not happening, then also the probability of alarm ringing is 0.001. Okay, so here it is important to take away is probability of A given B and A, because alarm is dependent on its two parent, probability of burglary and earthquake. So this is the Bayesian network, right? Whenever I was talking about Bayesian network, this is the Bayesian network only, because I am telling you that you have to write it with a random variable with respect to its parents. That is why, as the alarm has two parents, that is burglary and earthquake, that is why we have written like that, the probability of alarm given burglary as well as earthquake. Okay, now after the alarm, this alarm has two children, John as well as Mary. So this John will be dependent on his parent alarm, as well as Mary will be dependent on his parent alarm. So we will write this probability as probability of John given alarm. Okay, probability of John calling given that alarm will ring. So if true means probability that John will call provided alarm has ring, that is 0.90, and probability of John does not call if alarm rang, that is 0.05. Similarly, you can see about Mary. Probability of Mary will call provided alarm has ring is 0.70. Probability that Mary will not call provided alarm has rang is 0.01. So this is about the question. So any doubt about this example? Anything it is not clear about this Bayesian network?
Clear, sir.
Clear, right? Now, according to this Bayesian network, we have two questions. First question is, what is the probability that the alarm has sounded but neither burglary nor an earthquake has occurred and both John and Mary call? Okay, so what has been told in the question is alarm has ring and John and Mary has also call, but provided that neither burglary nor earthquake has happened. So what is the probability? So how we will find out the probability? We will find out the probability by this. So thing is John and Mary call. So we will write it like this: John and Mary, and alarm has rang, but provided there is no burglary and there is no earthquake. So that will be probability of John given the alarm, and probability of Mary Mary given the probability of Mary cause given the alarm into probability of alarm ringing when no probability of alarm ringing when no burglary as well as no earthquake has happened. But again we have to write probability of no burglary as well as probability of no earthquake. Okay, so this is our final probability statement of this question. So again I am repeating what has been told in the question, that John and Mary calls. Okay, John and Mary calls, and alarm has rang. That is why John and Mary calls. Okay, alarm has rang. Okay, alarm has rang. John and Mary has called. Provided that there is no burglary and no earthquake. That is why no burglary as well as no earthquake. So how we will write it? We know the probability of John cause provided alarm, that we know. Okay, probability of John provided alarm has rang. We know the probability of Mary cause provided alarm has rang, and also we know that probability of alarm provided no burglary as well as no earthquake has happened. And we also know probability of no burglary as well as no earthquake. So probability of John calls and provided alarm has rang, that is 0.90. Okay, this is the thing, because John calls, that is true. So we will take the true example. So John calls provided alarm has rang, so that is why 0.90. Now probability of Mary calls provided alarm has rang, that is 0.70. Now probability of alarm rang provided there is no burglary as well as no earthquake, that is this thing, because no burglary, no earthquake, but alarm has rang, so that is why 0.001. Now probability of no burglary and no earthquake. So what is the probability of no burglary? That will be equal to 1 minus 0.001, so that is 0.999. And what is the probability that there is no earthquake? 1 minus 0.002, that is why 0.998. So when you will multiply this, you will reach this answer. So any doubt in this?
No, sir.
Okay, now we have this second question. What is the probability that John call? Okay, what is the probability that John calls? Okay, so we are only interested in probability of J, but probability of J we cannot calculate it, because John is dependent on alarm, and further alarm is dependent on burglary as well as earthquake. So for knowing only probability of John, we have to deal with John and alarm thing, and then alarm and burglary and earthquake thing. So that is what we are doing. We are writing probability of John that alarm has ring into probability that alarm has ring, and probability of John that alarm has not ring into probability that alarm has not rang. So probability of John and alarm has rang, that we know, that is 0.90, and probability John and alarm not rang, that is 0.05. But probability of alarm, do we know? No, we don't know probability of alarm. For knowing the probability of alarm, we need to apply this Bayes theorem. And how we will apply probability of alarm? We will take all these 4 cases. Okay, how we will take these 4 cases? First we will see probability of alarm provided both burglary and earthquake has happened, into probability of burglary into probability of burglary and earthquake. Then probability of alarm provided that no burglary has happened but earthquake has only happened, and probability of no burglary and earthquake. Similarly probability of similarly probability of alarm provided burglary and no earthquake happened, burglary and no earthquake happen, and into probability of burglary and no earthquake. And last case, that nothing happened but alarm has rang, into probability no earthquake and no burglary. Similarly in this case also, we need to for knowing the probability of no burglary, we have to do this, that is no burglary no alarm burglary earthquake into this burglary earthquake. Similarly like this we have to do this. So we know this, we know this. Now what about probability of alarm provided burglary and earthquake? It is provided into probability of burglary earthquake, that we will do by multiplying both this burglary as well as earthquake. Now similarly probability of alarm provided no burglary and earthquake, then we will use this third case, and we will we will be multiplying with no burglary, that is 1 minus this into earthquake. Similarly, we will do the calculation, and we will be 0.90 into whatever the bracket, whatever you will be doing the calculation, into 0.05 into whatever you will be doing the calculation, and your final result will be this 0.0521. Okay, so is it clear to all of you?
No, sir, it is very confusing.
Very confusing. Okay, so Bayesian network, you understood the concept, right? That if a child is there and we need to know the probability of the child, then we have to condition it with the parents only. Okay, so here if we need to know the marginal probability of only the child, we have to condition with his parents. So this John has one parent, alarm. Now this alarm has two parent, burglary and earthquake. So we have to condition it. Now to know the probability of John cause, that will be equal to probability of John provided that alarm has ring into probability of alarm, right, plus probability that alarm has not ring into probability that alarm has not ring. So this is clear, right? This is your base theorem only. This is nothing but this is your base theorem only. Up to this it is clear, right?
Yes, sir.
Yeah, up to this it is clear. Now the problem is this alarm also depends on two parents, burglary as well as
Mm.
earthquake. Okay. Now when the alarm depends on burglary and earthquake, we have four cases. Okay, this is case 1, case 2, case 3 as well as case 4. Now again we have to condition our alarm probability with respect to burglary and earthquake. Into we have to multiply with our parents probability, that is burglary and earthquake. So that we will do for all the four cases. So first case is this case. So this case both are true. So both are true. So we will be taking this 0.95 into 0.01 into 0.02. Now here this second case 0.94 into this is true, 0.001 into this is false, so 1 minus 0.002. Similarly you will do the next two cases also. Now what about not ringing alarm? Not ringing alarm, what we will do, we will subtract 1 minus 0.95, so
9.
0.05 into whatever the burglary into earthquake. Similarly here also you will see what
No,
is
4
true and
cases.
what is false, and again you have to do this, and this is your total calculation. Okay.
Okay, sir. Okay.
Okay, so this is about Bayesian network, and this is about rules and parent-child relationship, d-seperation, and this is about completely about Bayesian network. Now we will be moving directly on to our question answer session. So topic which are week 8 assignment are based, random forest, AdaBoost versus gradient boost, and Bayesian network. So this is the first question. Uh, yeah, consider the Bayesian network given below. Which of the following statement is are true? B is independent of F given D. This is our Bayesian network. Okay, B is independent of F given D. Now A is independent of E given C. E and F are not independent. E and F are not independent given D. A and B are not independent given D. So any guesses for this? All the three rules will be applied here. All the three rules of d-seperation will be applied here. So any guesses? What is true and what is false? No guesses, right? Okay. Okay, so let's see. B is independent of F given D. So B is independent of F given D. So this, okay. Okay. So B is independent of F given D. So this will be dependent on our chain structure. Okay. Chain structure, what it tells is if a middle node is given, then X and Y will be independent. So here also same thing, that middle node is given. That is D is given. So let's forget about C. D is given, then what we know is if D is given, then this B is independent of F. So A is true. Now what about the second case? A is independent of E given C. A is directly related to E. So A and E are not independent. So this is the first statement. Now what about this? E and F are not independent given D. Now E and F are not independent given D. We will see this. E and F are not independent given D. So we will check this by Fox structure. So Fox structure, you can see if we have a middle node and we have two child nodes, that is M and Y, then given a parent, this child nodes are independent. Okay. So given a parent here, the parent has been given, that is D is given. So this E and F will be independent. Here it is written not independent. So again this is false. Now what about the last case, that is A and B are not independent given D. So we will be using our third rule. Okay. So what is the third rule? Our third rule is this rule, that if we have two parents and one child, then given the child, our parents will be dependent. Okay. So here our parents will be dependent. That means A and B will be dependent given D. Okay. Okay. 1 minute. Yeah. So last, am I audible? Hello. Am I audible?
You are audible.
Yeah.
Yes, sir, you are
Yeah.
audible.
Yeah. So last question was A and B are not dependent given D. So we will be requiring our third rule, uh, that is that is this collider structure rule. Okay. So that what does this rule suggest? This rule suggests that if middle node is given, then X and Y are dependent. Okay. But here it has been telling that. Here it has been telling that if given D, A and B are not independent, means A and B are dependent. So that is true, right? That if a child node is given, then this parent nodes are dependent. Okay, not independent is dependent. So this is also true. So A as well as B is your correct answer. So any doubt in this? We will be using all our three rules and we will see the we will be guessing our answer. Okay. Is it clear? Any doubt in this? Hello?
No, sir, it is clear.
Clear, right? Everyone, it is clear, right? No, sir. Means no doubt, right? Okay. It is clear, right? Sujit Kumar, it
Yes,
is
sir.
clear, right?
Yes, yes, sir.
Okay. Now let's move on to the next question. A patient goes to a doctor with symptom S1, S2 and S3. The doctor suspect disease D1 and construct a Bayesian network, D1 and D2, and construct a Bayesian network for the relationship among disease and symptom as the following. So this is the Bayesian network. Now what is the joint probability distribution in terms of conditional probabilities? That you have to find out. Okay. So A, B, C and D. What is the correct option out of A, B, C and D? Any guesses? No guesses. Okay. Okay. So I have told you how you should write your probability. You should write your probability that the first nodes are the root nodes. Okay, the first nodes are the root nodes. So root nodes has only marginal probabilities only. That means root nodes will use only this d1 is not influenced by any of its parents, right? d1 has no parents, so d1 will take marginal probability only. Similarly, this d2 has no parents, so d2 will also take marginal probability only. But what about s1, s2 and s3? This s1, s2 and s3 has parents d1 and d2, so that is why s1, s2 and s3 will take conditional probabilities. Okay, it cannot take marginal probability, but s1, s2 and s3 will take conditional probability. So s1 will be dependent on d1, so we will write p of s1, okay, into p of s1 provided d1, okay, and then s2 has two parents, that is why we will write probability of s2 provided d1 and d2 because it has both parents. Now what about s3? S3 probability of s3 has only one parent, that is d2, that is why d2, okay, and we have d1 and d2 has marginal probabilities, so probability of d1 and probability of d2, okay. And Bayesian network, what we will do, we will multiply all this. So probability of d1 into d2 into probability of s1 provided d1, probability of s2 provided d1 and d2, and probability of s3 provided d2. So what is the correct answer? Probability of d2 d1, so this is false because d2 and d1 are not related, right? So this is, that is why this is false, this is anomalous, so this is false. Now probability d1 d2 is right, s1 d1 is right, s2 d1 only, s3 d1 and d2. S3 has only one parent d2 and s2 has two parent d1 and d2, so that is why these two are anomalous. Okay, these two are anomalous, that is why this is also false. Now what about this? d1 and d2 is given, s1 d2 is given, s2 d2 is given, s2 only d2 is given, s3 d2 is given, s2 has d1 as well as d2, so this is anomalous, that is why this is false. Now last option, d1 is given, d2 is given, s1 d1, s2 d1 d2 and s3, so option D is your correct answer. Okay, any doubt in this? Any doubt in this?
No, sir.
Okay. Now consider the following data for 20 budget phones, okay, 30 mid-range phones and 20 high-range phones. Consider a phone with two SIM cards. Okay, and here the data is given for only one single SIM card, but here it is telling we have to consider two SIM card and NFC. Yeah, NFC data is given, but no 5G compatibility. Okay, so here we have to do bar of this and we have to do bar of this. Means single SIM we don't want as well as 5G compatibility we don't want. So that is the thing, and a high-end phone using the naive bias. Okay, the correct ordering of the phone type from the highest to lowest probability is. So by naive bias we have to find the probability. So first we will take class, first we will take budget class, and budget class we have three condition. Okay, one condition is it will have two SIM, second condition is it will have 5G it will have no 5G compatibility, and it will have NFC. So yeah, budget phone, and this is means this is a bar also you can use, or here it is use this this interrogation mark, that is bar, that is single SIM data is given, but we used to know two SIM, that is why bar of this. And now 5G is given, we have to go with no 5G, that is why bar of 5G, and then NFC is given, and again we have to just multiply the probability again and again. So how we will be finding out? This is a parent node, right? Budget this number of phone is a parent node, so probability of class. So budget phone we have 20 budget phone out of 20 plus 30 plus 20, that means 20 by 70. So probability of budget phone will be 20 by 70, and now our condition will come that probability that singles double sim provided that provided that two sim provided that it is a budget phone, so that will be 5 by 20. Why 5 by 20? Because 15 single phone is already there, so two double sim phone will be 20 minus 15, that is why 5 by 20. Now 5G compatibility, 5 phones are 5G compatible, that means 15 phones are non 5G compatible, that is why 15 by 20. NFC, we have to find NFC, that is 0 by 20. So probability is 0 because the NFC are 0 by 20, that is why 0. Your probability will come 0. Now about mid-range phone, you will do the same calculation. Mid-range phone, we have 30 mid-range phone, that is by 30 by 70 into your 2 sim by mid-range, non 5G by mid-range, and NFC by mid-range. So 2 sim by mid-range will be 10 by 30. No 5G by mid-range will be again 10 by 30, and NFC will be 15 by 30. When we will do the calculation, you will get this 0.0238. Now last thing about higher end phone. Now this first you will be calculating the marginal probability of the high end phone, that will be equal to 20 by 70, and then you will see the conditional probability of 2 sim by high end, that will be equal to 5 by 20. Then no 5G by high end, that will be equal to 5 by 20. Then NFC by high end, that is 15 by 20. So you will do the calculation, and this is your final answer, that is 0.0134. So here it has been told the correct order of ordering of phone type from highest to lowest. So we will be going from highest to lowest probability. So first will be our first will be our mid-range phone, then we will have our high-end phone, then we'll have our budget phone. So mid-end, high-end, and then budget. So option C is our correct answer. So is this clear? Is this question clear to all of you?
Okay, sir.
Clear, right? Everyone, it is clear, right?
Yes, sir.
Okay. Okay, so I hope it is clear. It is nothing but our this Bayesian network only. Here we have three parents. Okay, here we have three means three root nodes: budget, mid range, and high end. Okay, budget, mid range like D1, D2, and D3. Okay, and we have all this has three subset. Okay, so D1 has three things, that is this single sim 5G and NFC. Similarly in case of D2 as well as D3, or you can say this okay. Okay, so D1, D2, D3. D1 has three cases. Similarly, in case of D2, and similarly in case of D3. Okay. And you can say one of their parent is nothing but mobile phones. Okay, so this is nothing but the case of a Bayesian network. So you can calculate it similarly with this. So here you have D1 and D2 and D3, that is given, and then this all have three children each. So by that you can calculate the probabilities. Okay. So option C is the correct answer. Now talking about question number 4. Consider the following graphical model. Mark which of the following pair of random variable is independent. Okay. Option A is C, D. Okay, C and D. Okay. Option B is C and E. Okay. Option C is B and D. Okay. And option D is A and B. So any guesses for this? Am I audible? Someone is telling C, that is B and D. It is told independent, not dependent, right? Yeah, D. Yeah, D is the correct answer, because these two are root node, or you can say the main parents. And anywhere you have seen here this example as well as any example, these parent nodes are not dependent with each other. Okay, so that is why option D is the correct answer. And we don't know anything about C, that is why we can correctly tell that we can clearly say that A and B are independent. Okay, so option D is the correct answer. So it is clear, right? If there any condition is given about C, then you can think, but as there is no condition is given about C, so you can clearly say that the parent nodes are always the parent nodes, or the root nodes are always the independent nodes. So option D is the correct answer. Okay.
Okay, sir.
Now we are let's move on to the question number 5. Consider the following data for 500 instances of home, 600 instances of office, 700 instances of factory type building. Suppose a building has a balcony, power backup, and is not multi-story. According to name wise, it is of the type home, office, factory. Okay. Suppose a building has a balcony, a power backup. Okay, balcony, a power backup, and is not multi-story. According to the naive Bayes algorithm, it is of the type home, office, factory. Here nothing you have to do, you have to find the probability again, similar to this question. Okay, exactly similar to this question, you have to find the probability, and you have to check which of the three you will get the maximum probability, and whichever you will get the maximum probability, you will take the answer. So again it has been done like that. So here you can check probability of home given the back that you can calculate, that will be equal to probability of home into probability of probability of balcony in case of home, probability of power backup in case of home, and probability of not multi-storied in case of home. And again you have to multiply it, and you will get the answer. Similarly, you will do the same thing with this office as well as factory, and in this case the maximum probability you are getting with factory, so option C is your correct answer. So is it clear? Very similar to the third question, exactly similar you can say to our third question. Only difference here is it has been told that it has been given three condition, and according to this which of the type. That means here it has been asked that you have to find out the naive Bayes algorithm probability with which has maximum probability out of this three parents. So maximum probability is coming in case of factory, that is why option C is your correct answer. So is it clear? The calculation you
Sir,
can,
please,
yeah,
please explain it. Please explain.
yeah. This question is clear, right? Third question is
Sir, this question is clear. Yes.
third question is clear, right? Exactly similar to this question only. Here also same table, same type of table it is been given. Here it has been told that three condition are given here, that it will have power backup. Okay, your building will have power backup. Your building will have balcony, but your building is not multi-story. Okay, so what exactly is your type of building? That means they are talking about the probability, which of the three classes you will get maximum probability. The maximum probability which class you will get, you will say that is the type of building. Okay, now how you will find out? You will find out by probability of this probability of this home with three condition: balcony, multi-storied, and power backup. That is probability of home, that is 500 by 1800, right? Into probability of balcony provided home, that will be equal to 400 divided by 500. into probability of power backup provided home, that is 100 divided by 500, into probability of not multi-storied, probability of multi-storied is 200, that means 300 is not multi-storied, so into 300 divided by 500. So by that your answer will come 0.018. So same thing you will do for office as well as factory. So for office your answer will come 0.031, for factory your answer will come 0.034. So maximum is coming in case of factory, so that is why you will take the factory. Okay?
Multi-storage, it is given 2 by 5. It should be 3 by 5, no, sir?
Not multi-storied.
Not multi-storage.
Yeah.
Multi-storage is given 200.
Okay.
So, not multi-storage, it is to be 300 by 500, no?
Okay. So let's do the calculation. First is 5 by 18. 5 by 18
It is
into
okay.
4 by
4 by 5 is okay.
into not multi-story, that means 3 by 5.
3 by 5, no?
Yeah. Into
Yes, sir. But it is
power
given
backup.
2 by 5.
Power backup is 1 by 5. Okay, so 5
Here
by
it is
18,
given 2 by 5, no?
4 by 5, 2 by 5 is given, and 1 by 5. Okay, so this is wrong, I think. This is
Yes, sir.
yeah, this is wrong, so it will be 3 by 5. Okay. Similarly, you will do the calculation in case of this
Yes, sir,
also and this
understood.
also, and you will check the maximum probability where it has been covered. Okay,
It is okay, sir.
it's clear, right? You will check the calculation, and whatever the maximum it will come, and you will do the again it has been told for multi-story. So again here also the calculation has been wrong. It will be 450 by 60. Okay, this will be 450 by 60, that is 45 by 60, and here it is multi-story,
150,
means
15
it
by
will be 250 by 250 by 700, that means 250 by 700, that means 25 by 70.
25 by 70.
25 by 70, whatever the answer will come, you will take the you will whatever maximum probability will come, you will take that option. Okay, you please go and check on the calculation, whatever maximum you will come, you will take the answer. Okay.
Yes, sir.
Now, which of the following statement is are true? Random forest is an example of ensemble method boosting. Okay, option B, gradient boosting starts with a leaf. Option C, AdaBoost has 8 to 32 terminal nodes in each tree. And option D, gradient boosting gives higher weight to more accurate tree, whereas AdaBoost gives equal weight to all trees. So any guesses for this? No guesses? Okay, let's read it one by one. Random forest is an example of ensemble method boosting. No, random forest is an example of ensemble method but bagging, that is bootstrap aggregating. Random forest, we are first making a bootstrap sample, we are making a tree of that sample, given taking only subset of input variables. Okay, and we are creating tree for each bootstrap sample, and lastly we are aggregating, that is we are voting for the final prediction. So that is random forest. So it is not a method of boosting, but it is a method of bagging. Okay, so option A is false. Now gradient boosting starts with a leaf. Yeah, exactly, gradient boosting starts with a leaf, and that leaf is a average value for all your output variable, or your leaf is a leaf has a value that is average for the classification problem, and average of log odd in case of average for regression problem, and average of log odds for classification problem. So option B is true. Now AdaBoost has 8 to 32 terminal nodes in each tree. No, AdaBoost does not contain tree. AdaBoost contains stumps only. Okay, stumps means one root node and 2 leaves only. So AdaBoost has 2 leaves in its terminal nodes. So AdaBoost has 2 terminal nodes in each tree. So it has been told AdaBoost has 8 to 32 terminal nodes. So this is false. And last, Boosting gives higher weights to more accurate trees, whereas AdaBoost gives equal weight to all trees. So AdaBoost gives more weights to more accurate tree, whereas gradient boost gives equal weights to all trees. So this is also false. So option B is only correct. Option B is only correct. Okay. So any doubt in this? This is a pure theoretical question that has been discussed to you. No, C is not correct, but B is correct. The gradient boost has 8 to 32 terminal nodes in each tree, but AdaBoost has stump only. That means it has 2 terminal nodes or 2 leaves only. Okay, that is why C is false. Okay, I think it is clear to all of you, right? So let's move on to the next question. While using random forest, if the input data is such that it contains a large number, that is 80% irrelevant feature, the target variable is independent of this feature, which of the following statement are true? Random forest has reduced performance as the fraction of irrelevant feature increases. Random forest has increased performance as the fraction of irrelevant feature increases. The fraction of irrelevant feature does not impact the performance of random forest. So any guesses for this? Yeah, A, someone is telling A, Sandeep is telling A. Any other guesses? Okay, yeah, exactly. So if your input data contains more than 80% of irrelevant feature that will not contribute to the output, then definitely it will, what it will do, it will, as we are creating a tree of a bootstrap sample, in that bootstrap sample also we are considering only subsample of your input variables. So if large number of your variables is irrelevant to the output, then what happens, the tree will be more weaker and weaker. So our final prediction that will come will be irrelevant. So option A is your correct answer. Okay, now let's move on. Is it clear to all of you? Clear, right?
Yes, sir.
Okay. So a man is known to speak the truth out of 3 times. He threw a die and reports that the number obtained is 4. Find the probability that number obtained is actually 4. So this is pure probability question. Okay, so let's see how to solve it. So we are considering event and cause. Event is number 4 as obtained, that we are considering it as B, and cause is A, that is man reports that 4 is obtained. Okay, so we have been told to find the probability that number obtained is actually 4. Okay, so number obtained is actually 4, but the man speaks the truth 2 out of 3 times, and he throw a die and reports that number obtained is 4. Find the probability that number actually obtained is 4. So we will use our Bayes theorem. What our Bayes theorem tell is probability of B given A is probability of A given B into probability of probability of A given B into probability of B divided by probability of A. And how the probability of A is find out, that the man reports that 4 is obtained, that is found out by probability of A given B into probability of B plus probability of A not given B into probability of not B. Okay, so we are interested in finding probability of B given A. So that is number 4 is obtained, and the man given that the man reports 4 is obtained. Okay, now how we will find out that probability of A given B. What is probability of A given B? Probability of A given B is the truth. Okay, the man speaks truth. So that is probability of A given B is the man reports 4, and given that number 4 is obtained. That means the man is speaking the truth. So that is 2 by 3. And what is probability of A not given B? That is the man is telling the false. That means 1 minus probability of A given B. That is 1 by 3. What is probability of B? Number 4 is obtained. That is, as he is throwing a dice, that is probability of each number, maybe 1 or 4 or whatever the probability is, 1 by 6. So probability that number 4 is obtained is 1 by 6, and probability that number 4 is not obtained, out of 1 to 6, 4 has not obtained. That means 1, 2, 3, 5 or 6, out of this 5 anything is obtained, that is 1 minus probability 4 has obtained, that is 5 by 6. So you will straight away apply your Bayes theorem. Probability of A given B, that is the man is speaking truth, that is given, that is 2 by 3. You will put it. Probability of B, that is 4 is obtained, that is 1 by 6. That is also we have calculated, divided by this 2 by 3 into 1 by 6 into probability that the 4 has not obtained, and 4 has not obtained, that is the number 4 has not obtained, and also the man is reporting that 4 has obtained. Okay, so we have to that means the man is telling the lie. That means 1 minus 2 by 3, that means 1 by 3 into probability that not 4 is obtained into 5 by 6. Wherever you will do the calculation, your answer will be 2 by 7. So option D is your correct answer. This is a question of pure probability. So pure probability and Bayes theorem. So this is how we will solve this. Okay.
Okay, sir.
Now question number 9, considering the AdaBoost algorithm, which among the following statements are false. In each stage we try to train a classifier which makes accurate prediction on any subset of data points where the subset size is at least half the size of data set. Okay. In B is, in each stage we try to train a classifier which makes accurate prediction on a subset of data points where the subset contains both the data points which were misclassified in the earlier stages. Okay. Option C, the weight assigned to an individual classifier depends upon the number of data points correctly classified by the classifier. Option D, the weight assigned to an individual classifier depends on the accuracy of the classifier. So any guesses for this? No guesses? Okay. So B as well as D is your correct answer. So first thing, in each stage we try to train a classifier which makes accurate prediction on any subset of data points where the subset size is at least half the size of data set. No sense, right? Second thing, in each stage we try to train a classifier which makes accurate prediction on a subset of data points where subset contains more of the data points which were misclassified in the earlier stage. So this is a principle of boosting ensemble method, right? We are giving more weight to the misclassified points and we are giving less weight to the classified points. So option B is correct. See, the weight assigned to an individual classifier depends on the number of data points correctly classified by the classifier. Weight assigned to an individual classifier depends on the number of data points correctly classified by the classifier. Okay, the weight assigned to an individual classifier depends upon the accuracy of the classifier, right? So option D is correct. The weight assigned to an individual classifier depends on upon the accuracy of the classifier. Okay, so this is correct. So option C is false. The weight assigned is not based on the number of classified point, but rather depend on the error rate, right? Means accuracy of the classifier. So by that the weight is given according to the accuracy of the classifier and not on the number of misclassified or classified points. So option C is also false. So A is false as well as C is false, and B and D is right. So again, let me remind you the principle of AdaBoosting. So AdaBoosting, we are giving weight to at two stages. First stage is we are giving weight to the stumps such that the more is the accuracy of the stumps, the more we are giving the weight to the stump. Okay, first weight. Second weight, we are giving weights to the misclassified point to create the data set for the next classifier. So more we are giving more weight to the misclassified point and less weight to the less misclassified point, so that whenever our next subset is created, whenever our next data set is the new classifier will work more on the misclassified points. Okay, so these are the two principles of ADA boosting. So that is why option B as well as option D is right. Okay, is it clear? Okay, so let's move on to
Accuracy and accuracy and correctly classified points. What's the difference between those C and D?
okay, difference between C and D. The weight assigned to the individual classifier depends upon the number of data points correctly classified by the classifier. Actually, yeah, accuracy, if you are terming accuracy in case of misclassified and classified point, then C is right. But if you are trying to classify accuracy in some other context, okay, so in that case option C may not be right. Maybe you want your classifier in case of precision or something like that. So for that your option C is not correct. So that is why C has been not taken correctly. Okay, because we are giving weights to the tree based on our whatever our aim is, whatever we want to increase in our final prediction. So that is why option C is not classified correctly. Okay.
Okay.
Now question number 10, statement 1, Bayesian network always need to be directed acyclic graphs. Okay. Statement 2, each node in a Bayesian network represents a random variable and each edge represents the conditional dependency. Which of these are true? Both the statement are true. Option B, statement 1 is true, second is false. Option C, statement 1 is false, statement 2 is true. Option D, both the statement are false. So yeah, option A is the correct answer, because Bayesian network always need to be directed acyclic graph. Okay, directed acyclic graph means it must have relationship between your parent node and child node. Okay, that is how we can create this Bayesian network, and it will have a clear edge. That means it must have a clear link between the two nodes. So that is why it must be denoted with a direct acyclic graph. Okay. Second thing is, each node in a Bayesian network represents a random variable. Exactly, each node represents a random variable, and the links or the edge. Okay, two things are there for nodes. Vertices are also used for this links. Edge is also used. So these are the terminology you should remember. Again, I am repeating, for nodes, the vertices are also used. For this links, edges are also used. Okay, it is also called edges, means links are also called edges. The nodes are also called vertices. Okay, so same thing. So this links or this edges represents the conditional dependency. So option A is your right answer. Yeah, option A is your right answer. Okay, so any doubt in this? I hope no doubt in this question.
No, sir.
Okay. So by this I am ending the session for today. I hope you guys don't have any doubt, right? Any doubt in any question or anything?
No, sir.
Okay. So by that I am ending the session for today. We will meet on the next Monday. Okay.
Okay, sir. Thank you, sir.